Okay, so they say not to start a talk with a joke, as I just did, but to start with a promise. So if you make a promise to the audience and you promise them that something will happen at the end of this half an hour, that maybe you get their attention. So here is my promise for you. At the end of this half an hour, you will be able to understand how to invert a matrix with complexity n square. So if you have a n by n matrix and you want to find the inverse, you know that you need to do a certain number of operations, right? And typically we say that we need to do a number of operations that grows with the cube of n. Now, there are algorithms that can lower this exponent, but let's say roughly n cubed with digital algorithms, okay? And there is no known digital algorithm that can invert a matrix with complexity n squared. So I'll give you some intuition on how this will be possible with a different paradigm, okay? If it is not digital computing, it will be analog computing. And then I will go through some applications for wireless communications because this is the topic of this event, right? Okay, so many years ago, decades ago, there was this fight between digital computing and analog computing, and digital computing won because of its benefits that we all know today. So the versatility in representation, you can represent anything, any sort of data with zeros and ones. And from the security perspective, there were a lot of talks today about security and storage flexibility also. But we became extremely excellent in designing digital computers in the last decades, but there are some fundamental limits that we are sort of almost hitting today, right? So for example, the clock speed is a fundamental limiting factor, and with digital algorithm also, you need to do a certain number of operations, and how many operations per second you can do, this is limited by the clock speed. And there is the concept of computational complexity. So to solve some problems, you require at least a certain number of operations, and those problems become unfeasible for high input sizes. And a third bottleneck is the fact that our world is analog. Everything we touch, we see, we hear, it's analog signal. So whenever you need to process something digital, you need to go through some analog digital converters and digital analog converters. And in some applications, these devices are quite expensive. For example, in wireless communications, this happens inside the RF chains, okay? And you have these ADCs and DACs that are very power hungry. Their power consumption grows exponentially with the resolution. And so what if we could do some operations directly in the analog domain, working with signals that we can see and touch? And very recently, there has been a revival of these analog computing concepts. Also, Shannon wrote a paper, by the way, in analog computing, which is a mathematical theory of the differential analyzer, which is less known than the other mathematical theory. But he was working this differential analyzer, which was a mechanical machine computing differential equations that, of course, today it's extremely obsolete. But there has been a revival in doing some sort of digitally inspired analog computations at the speed of light, working mainly with electrical signals or electromagnetic signals, okay? And this has been due to some advances in the field of metamaterials. So you could design some materials with very specific responses, such that, for example, the wave transmitted or reflected by this material is a specific function of the impinging wave. And for example, you could compute the second order derivative of the impinging wavefront for free at the speed of light, which for us it's infinity, right? We are not considering any quantum effects in this talk. Or also very known classical systems that can do analog computations are lenses. So you can work with in the optical domain, and you have this very nice system that can compute at the first step the DFT of the Fourier transform of the impinging image, and then you could do some operations like filtering to do edge detection, and then you could again transform in the space domain. And also in the field of memory arrays, there has been a lot of work in what is called in-memory computing. And these crossbar arrays can be used to do matrix operations, in particular matrix vector products with DC signals. So today we need to narrow down a bit the scope of the talk. So we will consider computations that can be done with microwave signals. Microwave signals are like 300 megahertz, 300 gigahertz, okay? What we use commonly for communications. And we are considering analog computers that process linearly these signals. Because in general, microwave components that we use, our world is linear. Microwave signals interact in a linear way. And so let us try to abstract this concept that we call microwave linear analog computer, MILAC. So let us consider a black box, a blue box, that can be literally anything, a microwave linear network, anything including linear components. It can be made by metamaterials or commonly used RF components, okay, transmission lines, impedances, capacitors, inductors, all these components, phase shifters are linear. And this is modeled as a black box for the time being, which has n input ports, where you apply n electromagnetic signals as the input, and it has m output ports, where you read those signals. And in general, the output signals will be a function of the input signals. And the key factor is that this function can be computed instantly as the waves propagate inside your black box, okay? So to give you an intuition on why this could be interesting, how many of you work with electromagnetic simulators? Anyway, if you try to build an antenna and you design this piece of hardware, okay, often a typical operation you want to do is to apply some input in this antenna and check the values of the electromagnetic field in some points of this piece of metal you are designing, okay? And typically you do this with some electromagnetic solvers, simulators, solving Maxwell equations, and you need to wait a lot, okay? You need to wait a lot, typically. But if you build this component, you can actually physically input your electromagnetic signals in the input of the antenna, and you can immediately, the electromagnetic field in the point you want is immediately created, okay, in the analog domain. So electromagnetic field interacts at the speed of light, and they instantly, for free, compute something that would be difficult to, not difficult, it would require a lot of time to compute digitally. So let us first of all consider the case when this black box is non-reconfigurable. So you design, you have that, and it's fixed. So since it's linear, okay, the output signals V, V1, Vm, that can be stacked in a vector V, will always be a linear transformation of the input signals that are U1, Un stacked in a vector U, okay? Where the transformation matrix W will depend on what you have inside that black box. And in this case, what's the gain? Well, you can compute a matrix vector product that would require digitally NM operations, if you trivially compute it with, as we know how to compute matrix vector products. But in the analog domain, this can be done instantly. Instantly as you apply the input signals. So a specific example of this case is called over-the-air computing, right? If you imagine that your black box is a huge black box, the wireless channel between multiple transmitting antennas and multiple receiving antennas, at the receiving antennas, you directly have the sum, because of the superposition principle, of the transmitted signals. And this is, in some literature, is referred to as over-the-air computing, and it has interesting application on federated learning, for example. where you want to acquire data from multiple sensors, but you do not care about the data of the single individual sensors, but you want, for example, only the average, okay? But let us try to make things a bit more interesting for us, because we remember my promise. I want to teach you how to invert a matrix, and matrix inversion is not a linear operation. So let us say that we have some tunable components inside our black box. And these tunable components can be, in general, anything, any RF tunable component. Some examples are pin diodes, okay, which are impedances can be short circuit or open circuit, or varactors, which are capacitors with variable capacitance, and therefore can be considered as impedances with variable value, okay? And let us say that you have K of such tunable parameters inside your black box. So in this case, the output V will always be a linear function of U, because remember, I consider only linear networks to make things easy. But the linear transformation matrix W can be a nonlinear function of these parameters, magically, okay? So the output will always be linear, a linear function of the input, but can be a nonlinear function of those parameters, okay? Even if our network is linear. And to convince you of this fact, let us study an extremely simple circuit. Everybody studied this. Everybody who has a bachelor degree in electrical engineering knows how to study those circuits and how to get the output voltages V1 and V2 as a function of the voltages of the generators, U1 and U2. Where we have those four G are conductances, the inverse of resistors. So you see that the outputs are there, V1 and V2. This, by the way, works also if I do this, and I can point this. Didn't receive enough attention today, but this is magic. So the output is a linear function of the input always, but you see that is a non-linear function of the values G11, G12, because they appear at the denominator. And this is very interesting. We will use this concept to do matrix inversion. So how to do this matrix inversion? Let us consider now a more specific example of our black box. So far, I have been very general, but now we need to go into the details. So let us consider a very general case in which we have this. The blue box is a multi-port network. It works. Where I interconnect every port to all the others through some impedances, okay? Here they are represented as Y admittances, but it's the same. And these admittances, let us assume that we are tunable. We can set them the value, are reconfigurable. We can set them the value we want. And let us say that we input some signals here at the input ports through some voltage generators. The signal generators are commonly represented through some voltage generators with a series impedance, which has a serious impact in RF circuits. That's why I'm considering it here. And let us say that we measure the voltages here in the output ports with some RF probes, okay, that have input impedance Y0. Now, it is possible to show that the question is, what's the relationship between the output signals and the input signals? So the relationship is quite complicated. It is given in these three formulas. So bear just 1 second with me. We should define, as a function of our admittances, Yij, we should define the admittance matrix Y of the port. Then we should partition these in 4 blocks, A, B, C, D. And then the output will be this function. So will be a linear combination of the input U, but will be a function of all these matrices. So the output function, it's a very complicated function that involves matrix inversions, matrix products, okay, which are computations that require n-cube complexity. But the output V, in this way, can be computed instantly. As soon as I apply the input signals to my network, I can instantly measure the the output signals. Of course, the speed of light is not infinity, so we will need some time for the signals to propagate. But for us engineers, that's considered instant. And the question is, okay, why should I care about computing this extremely ugly function of A, B, C, D? Okay, this function resembles by extremely nice mathematical coincidence, to which I'm extremely grateful, because otherwise I couldn't publish anything out of this. This resembles the LMMSE, linear minimum mean square error estimator, for a linear observation process. So if you observe the vector y as a function of an unknown vector x, and where there is also some noise, okay, and we assume that we know h, an extremely common problem is to estimate x given y, okay? This is, of course, also in MIMO detection, if you are familiar with wireless communications. And a very good solution to estimate x is this formula, which is a function of y, the observed vector, h, assumed to be known, and Cx is the covariance matrix of x, and Cn is the covariance matrix of n. You see that these two equations are extremely are the same. And if you still are not familiar, not convinced about the usefulness of this LMMSE, you are surely familiar with a special case of it, which is this one, where yeah, so it's a special case. You see, you can set Cx to the identity and Cn equal to 0, and then you get this case. And this is also called least squares, for example. All of us studied this thing. And the interesting part is now that to compute this object, you don't need to do some matrix inversions or matrix-matrix product. So you don't need a computational complexity growing with n cube, but you need only to reconfigure your components in the network, because once you reconfigure them, the output is computed instantly. And the complexity to reconfigure the components, it can be shown in the paper, that is just n squared. Now, this has interesting applications in MIMO, because that expression is an operation that we often want to do in MIMO. It's referred to as zero forcing beamforming when you apply it at the transmitter, or zero forcing combining when you want to do detection at the receiver. So today, this linear precoding or combining scheme is considered to be very practical compared to, for example, maximum likelihood estimation, which is non-polynomial complexity. But if we increase the number of antennas, so today we have talked for 15 years about massive MIMO. Today we talk about gigantic MIMO, where we have a huge number of antennas. Then even complexity of n square is prohibitive, because in wireless communication, you have often at the transmitter some symbols S, and you want to precode them to compute the transmitted signal X at every channel realization. So to compute this at every coherence time, when you have thousands of antennas, then it's considered to be prohibitive. In this way, you can do that with the reduced complexity. How? Well, just at the transmitter side, you will have the input signals in your microwave network will be the signals coming from your RF chains carrying the symbols you want to precode. And you need to attach at the output ports the transmit antennas. And the signal at the output ports will automatically will have this expression, which is known as regularized zero forcing beamforming. At the receiver, the dual thing can happen. So you will have the input signal in your network will be the signals that you receive at the antennas. You can combine them in the analog domain with your network, and then you can decode the output directly. So you can use the output directly for detection. So you need to attach the receiving RF chains to the output of the network. So, so just to give you some numerical, to quantify the benefit of this approach, consider you have M antenna base station and you want to serve N users with zero forcing beamforming. And this is the sum rate that you get as a function of the computational complexity required to do that operation. And we put there some huge values of users and antennas. So this means, for example, I have 1,000 users and 4,000 antennas. And in blue, you have the curve obtained with digital, with a fully digital architecture, okay? The numerology of 6G is expected to be around here. In red, you have the curve for our MILAC approach, okay, where you do pre-coding in the analog domain. So you see that you can achieve the same sum rate with a reduction in computational complexity of 4 orders of magnitudes, or with the same computational complexity, you can achieve a super higher sum rate. So now the benefit, to summarize the benefit of applying this MILAC-based beamforming, so pre-coding in the analog domain, we identify four main benefits. So you need a less RF chains. First of all, RF chains in wireless are very expensive components. You want to avoid them because of the cost and the power consumption. And so in this case, you just need as many RF chains as the symbols you want to transmit. And then at each RF chain, you will have to transmit one symbol. Not exactly the symbols, not a linear combination of them. So if your symbols are drawn from a constellation, which is QPSK, for example, you will just need to sample the real and imaginary part of the constellation with 1 bit. So you can equip your RF chains with extremely low resolution ADCs and DACs at the transmitter and the receiver. And at every symbol time, as I said, at every symbol time, we have new symbols S, and we need to compute this pre-coded version of the symbols. Okay, these happen extremely frequently, and has a computational complexity of a matrix vector product if you do that in the digital domain, but now is no longer required. And also at every channel coherence time, okay, you would need to compute a matrix inversion if you do zero forcing in the digital domain, but here you also avoid that complexity because from the cube, it becomes the square. So just to conclude, the four main messages of my talk, in case you fell asleep in the meanwhile, are it is worthwhile, I believe it's worthwhile to explore alternative computing paradigms rather than digital, because digital is about to reach a plateau, let's say, in power consumption, dimensions, and so on. And microwave signals can be used to perform efficiently very useful operations, okay? And n-by-n matrix can be inverted with complexity n square, while no digital algorithm is known that can do that. Now, the exact details on how you should design your tunable components, their input signals, and the output signals are given in the paper. But my promise was that you will be able to understand how to, not that you will know how to. And then there are interesting applications of all of these in MIMO communications, of course, because we use microwave signals to communicate, and we typically want to do that LMSC operation very often in MIMO. This concludes my talk.
Thank you very much for this inspiring talk. Are there questions? Yeah. Many. Okay. Yep. We have another one.
Thanks. So matrix inversion is something you practically never do numerically because it's so unstable. So what you usually do is you solve a linear equation system. And since you are having a highly structured problem, I would say the complexity is below n cube. Not n square, but it should be below the n square you're using as a reference for your problem. Because as I said, you don't invert a matrix. If you can avoid it, it's very, very unstable numerically.
Yeah. So n cube is a reference value, and for me at the beginning it was interesting when I found this strategy of achieving matrix inversion in complexity n square. Now, as you said, it's unstable, and also a problem we typically have in wireless that when we do that precoding based on H, is that H is not the true channel, right? H is an estimate, very noisy estimate. So now we are wondering, we are doing the next step, okay? This paper was very theoretical. We were focusing more on the benefit from the computational point of view rather than the applicative performance. Now we are investigating, so let's say we have a noisy channel estimate. What can we do better than practical strategies that do not even invert that matrix? Yeah.
Very nice talk, and I agree with you, by the way, that the matrix inversion is never done. I mean, this is why we have all the filters and such that kind of just track the track these channel values and whatnot. So yes, it's a very good point. My question is, if you go back to your slide where you have the inputs and outputs, yeah, that's good. Yeah, the microwave network. Are you effectively trading off time for space here, is what I'm wondering. Space meaning the physical footprint of the device that is this microwave network. And also, can you comment on the size of such device, not just the scaling? I work a little bit on the optical chips, and there, you know, the footprint of optical waveguides is typically measured in hundreds of nanometers, while footprint of a typical FET transistor on a microchip that does digital processing is, you know, much smaller than that, 15 nanometers. I think, because I'm not sure what the current record is. Maybe Edward can tell us, but it's like 5. I think 5 is the smallest chip that they have in Taiwan for making the memories, and I think it just can go even smaller than that. So can you talk about the footprint and the cost in those terms? Because I don't think you're accounting for all the costs on that chart over there. It's a wonderful chart. It's great work, but I think you need to consider the costs.
Yeah, thank you. Yeah, I'm sure you're not accounting for the cost. Yeah, now the prototyping of this structure is still under work. I could envision that like the ports will be spaced approximately lambda half. Okay, so if you work with lambda the wavelength. In microwaves, let's say lambda is 10 centimeters. So it depending on the number of ports you have, the footprint will scale. So there, for example, N input and M antenna in the output.
Yeah, but you have like 4,000 times.
Yeah. No, here I assume, huge number. Well, when you have a base station with 1,000 of antennas, then those antennas will be, let's say, spaced lambda half. And yeah, no, this is assumed to be a base station, on top of the buildings, but okay, let's be more practical then. Let us say that you use, I don't know, millimeter waves. The wavelength become 1 centimeter at 30 gigahertz, right? So the lambda is 5 millimeters. And then let's say that it's a square, the base station. So the size reduced by a square root. So now it's maybe a bit better. Yeah. No, of course, we started from a small scale prototype now. And yeah, I just was curious about what can we compute with microwave signals. If we can go beyond the capabilities of digital computations, then yeah, I don't envision that in 6G this will be standardized 4,000 of antennas. But the concept of 4,000 of antennas at millimeter wave, I didn't come up with that. It's a trend where we are going to, because yeah, to enable more rates in multi-user systems. But yeah.
Yeah, I think the argument is clear. I have also another question about this. So usually, if you try to load your microwave networks with the numbers, for example, with the current channel states that you need, no? So you need to somehow update that. How fast can you do that? Because I remember from my early MIMO days, 25 years ago, that this was a heavy issue to multiply in analog domain a complex number with the data streams that are going to, with the RF signals going to the antennas. So how fast can you do that?
Yeah, so I do not update my metrics at every single time of the data stream, but every channel coherence time. So it's a concept similar to a RIS, where you want to reconfigure a RIS with those tunable RF components. RIS is a reconfigurable intelligent surface, which has been a popular topic in wireless communication in the last 5 years. So it's a similar concept to that. So in those, actually my background is in RIS, and this all research is inspired by what I learned working on RIS during my PhD. And so also in RIS, you had these microwave structures that were reconfigured at every channel coherence time to do what? To steer the beam toward the users and serve also multiple users. Now, we talked about the same concept but applied at the transmitter side.
Right. I get that. So you don't need to do that fast. But
not at every single time.
So it
but
will.
At
so
channel.
Now you won't use that like your pocket calculator to do some computations. You would use it in the wireless context.
Yes.
Mainly.
Okay. Yes. Only some
I think
calculations.
This is also something that corresponds to the discussion about space. No, perfect.